remote placement of data, which I'll talk about in a second. So there is another type of form factor that I'm very interested in, and this is not the official title, but I've come up with it, NVDIMM PCIe. Basically an NVDIMM that hangs off the PCIe bus. Now, my son, who's an expert on all things persistent memory, and that's a picture of him here, when I told him about NVDIMM PCIe, he looked at me and said, that's either blucky or awesome. And blucky is basically a combination of blah plus yucky. I'm putting this word out there because I'm hoping I get it back in some like press announcement or email or something, that someone will use blucky, and I'll be like, yes, yes, I'm not. So these are devices that hang off the PCIe interface, but they actually behave quite like an NVDIMM in the fact that they're memory addressable. Okay, and I'll talk about a little why they're blucky and why they're not, or why they're maybe awesome in a minute. Microsemi, we have this device here. I got permission from my friends at Everspin to include one of their products, just to show we're not the only people out there with this kind of thing. And so there's some interesting things that we can do with this. Now, what is persistent memory? What is an NVDIMM on the PCIe channel? It's memory on the PCIe channel. What is memory on the PCIe channel? It's a bar. Right? For those of us who know PCIe, it's a PCIe bar that just happens to be able to store the data or maintain the data that's written or to that bar across power cycles. Okay? Now, it's kind of lucky because accessing the PCIe bar using load store semantics for most processors is pretty bad in terms of performance. If I write a piece of code on an x86 and say, hey, just read or write some addresses that are on a bar, and I go measure that performance, the latency is pretty good, but basically because of the QDEP1 nature of it, I don't get a lot of good bandwidth. There's a way we solve that. It's called a write combine. So in PCIe, when you do write combining, you're actually basically buffering to get around the problem. So why would we then put NVDIMMs on the PCIe? And I think where it gets interesting is as we move to the world of heterogeneous computing, where there's more PCIe devices that are attached to the processor that maybe want to communicate between each other, as opposed to necessarily always going through the CPU, then there's actually some pretty interesting things that we can do here. I don't have time to go into it today, but at Storage Developer Conference in 2016, and this paper is publicly available, I talked at more length around what this kind of device operating as a PCIe attached NVDIMM can do in things like an NVMe over Fabrics acceleration write cache environment. Right? Using this kind of device as a persistent memory device that's attached to a PCIe switch, rather than where you typically put an NVDIMM, which is up there. Oh God, it was a little higher. So this is one example, and there's quite a few other examples that we're kind of working through, and I find it very interesting because it's a very different way of looking at where we can put the persistent memory. And I don't think it's a one-size-fits-all. There's definitely going to be times when an NVDIMM makes more sense, but I think there's also times where this has some compelling value, especially when we integrate it with things like RDMA NICs, FPGAs that have acceleration functions, but also have DMA engines and maybe large exposed memory regions, GPGPUs, and we do know that the cloud vendors of the world are getting very interested in these heterogeneous environments. We have Microsoft's Catapult program. They've spoken publicly quite a bit about how that FPGA is being used to do acceleration. We know that some of the other large data center companies on the planet are also very big on things like heterogeneous compute. Okay? We can tie that into things like NVMe, and we can do some interesting things around the NVM programming model as well. And this is something that we need to really discuss. Andy mentioned there's a site called pmem.io. And because this is I/O memory, I've also registered a site called iopmem.io. If you go there right now, all it does is there's a little bit that goes, hi Andy. That's literally all I have on that website right now. But one of the ideas that we have is to discuss, as a community, does this kind of I/O persistent memory seem interesting? Is it worth doing some work on, and do we need to maybe do some work like we did with PMEM for IO PMEM? Or maybe we call it something else or whatever. But I think there's some interesting things that can be done there. So that's something that's worth exploring. So I want to kind of finish off with a quick discussion around coherency. This is a famous quote from the song Edwin Starr. I know I'm not going to try and sing it, but you know, war, what's it good for? Absolutely nothing. Coherency, what's it good for? And the answer is absolutely loads. Because if you have coherency and you're sharing memory across a system, the way that we handle that in a non-coherent environment is typically by pinning memory, get user pages, DMAs, context switches, going from virtual to physical addressing. It's quite a pain. I see some heads nodding, so people who work in this space of acceleration and heterogeneous compute seem to agree with me. I had the privilege of doing an early CAPI project. CAPI is a coherent interface on IBM Power 8. I did this a couple of years ago, and it was so much fun to write software for accelerators using CAPI. Now, you know, CAPI has its own issues in terms of vendor lock-in, but it was very interesting to write a driver for a PCI accelerator and then basically write no driver for a CAPI accelerator. So that's kind of where my eyes went, wow, this is awesome. And you were actually passing virtual addresses to the accelerator because it had the translation built in. It could talk virtually. So that was pretty interesting. So there's a lot of really cool things we can do. Most of it involves simplifying software. And to Andy's point earlier and my point earlier, if we want low latency, you've got to get software out of the way. So hardware supported coherency is very good. You can see Jim's coming. I'm not going to cover this slide. Very quickly, call to arms. There's lots to do. Is it Sisyphean? I don't know or not. Right? But there's a lot of work to do. Hopefully it's not Sisyphean. In fact, hopefully we'll repeat ourselves. But it's very exciting. This is my daughter. She's very excited, and I'm very excited as well. Very last point. I think where we're going is a world where storage, as we know it, could disappear. I'm not going to say that's going to happen, and that if it does, it's a very long-term goal. But let's imagine we go to the world where everything's MApped. Like I basically go MApp everything in the world, please. So I did some fun back of the page calculations. 64 bits is pretty common in a processor these days. If you assume that that's a flat address space, that gives us 18 exabytes. There's already some hyperscalers in the world who've probably beaten this number, right? So they couldn't even address all their data flat, even if they wanted to. The projections for IDC for data in 2025 is 180 zettabytes. So I need someone, Intel, can you build me a 73-bit address space processor, please? Let's round it up to 74, just to make it even. That's all I got. I don't know if we have time for questions. Thank you very much, everyone, for your time.
Thank you, Stephen. Very entertaining speaker, always. So I knew that for sure you'd be talking about that you can't get rid of latency. You know, that was predictable. Next, we have a break. We have a lot of us in this room. I think there's a body count of 380. So it's only a 15-minute break. So we're going to get started on time. But you know, you also have the option to phase yourself with the breaks if that's what you want. But we're officially on break now. We'll see you back here at it's actually 10:35.